Good morning, good afternoon, and good evening. My name is Arthur Holland Michel, and I am an associate researcher in AI and autonomy at the Security and Technology program here at UNIDIR. And I am delighted to welcome you to this side event to the 2020 group of government experts on lethal autonomous weapons systems. Before we begin, I just want to confirm with our tech support that my audio and video are coming through.
Yes.
Wonderful. So our topic today is predictability and understandability in military artificial intelligence. And I am truly delighted to be joined by Dr. Pascal Fung to help guide us through this important topic. Dr. Fung is the director of the Multidisciplinary Center for Artificial Intelligence Research at Hong Kong University of Science and Technology, where she is also a professor of electronic computer engineering and computer science and engineering. She is an elected fellow of the IEEE and the International Speech Communications Association. An early pioneer of using statistical modeling and machine learning for natural language processing, she co-founded the Human Language Technology Center and holds a long list of high-level accolades and expert advisory positions. Thank you so much for joining us, Dr. Fung.
Thank you, Arthur.
So here's the plan. We will chat for about 30 minutes in a sort of fireside chat style discussion. And then we will have some time at the end for audience questions, which you can submit using the question and answer function in your Zoom app. First, though, I'd like to give a little background on our discussion. In the debate on lethal autonomous weapons, it is very common to hear people speak about the need for these systems to be, quote, predictable or understandable or explainable. This suggests that any path that is ultimately taken to address the use of lethal autonomous weapon systems, or laws as we sometimes refer to them, must account for what is sometimes known as the black box dilemma of AI that is unpredictable and not understandable. And so earlier this year, we at UNIDIR set out to try and unpack and demystify these concepts of the black box dilemma. And over the course of researching this topic, I was actually lucky enough to claim a spot on Pascal's very busy calendar. And we had a discussion that would end up being tremendously influential for the report that UNIDIR actually just published on this very topic yesterday. The report is called The Black Box Unlocked. And you can find a link in the sidebar of your Zoom right now. It is a report that goes very much into detail on many of the topics that we'll be discussing today. As a quick aside, I should note that we here at UNIDIR believe that many of the considerations in the discussion on lethal autonomous weapons actually extend beyond lethal autonomous weapon systems as narrowly defined, to include other military applications of artificial intelligence, such as decision support and targeting support tools. And to that end, I just want to flag that UNIDIR recently published another report, Modernizing Arms Control, Exploring Responses to the Use of AI in Military Decision-Making, that explores whether such AI-enabled military applications could be particularly risky or destabilizing, and provides an initial exploration of whether existing arms control tools may be able to help address these risks. I should also note that both of these studies were produced by the Security and Technology program at UNIDIR, which is very generously funded by the governments of Germany, the Netherlands, Norway, and Switzerland, as well as by Microsoft. Now, figuring out how to address the black box dilemma, the topic of today's discussion, starts with an understanding of exactly what it is we're talking about. And that's where we turn to Pascal. So Pascal, I want to talk first about what it actually means to say that an autonomous system is, quote, predictable. I mean, to me, it seems like a fairly straightforward concept, but it turns out that there are, I guess, different types of predictability. So first, what does it mean in the strict literal technical sense of the term?
It just means whether the system is going to behave the way we think it will behave. But predictability also, depending on the nature of the system built. So if it's built by a if it's a rule-based system, then it can become even deterministic, meaning that you know exactly how the system is going to behave according to the rules that have been programmed into the system. So that's deterministic. But statistical systems or machine learning based systems, they can exhibit a range of behaviors according to the input. So they can be, they are not deterministic and they can be less predictable, even though they are predictable still within the range.
Got it, I understand. So that though, you know, the ability to perform on new data with the same level of accuracy as the system exhibited previously. So, you know, you have a toaster oven and it cooked your toast perfectly yesterday, and so it'll probably do the same today. You know, I guess is not the only sense of predictability or unpredictability that is relevant when we talk about autonomous systems. So can you talk about the other sense, what we might refer to as sort of operational unpredictability?
So you just mentioned it. So autonomous systems that have been trained using machine learning modules, they are trained with a lot of either simulated or collected data. And these data, of course, we hope that they are as varied and as realistic as possible, and they will correspond to the actual field operations. But if they are not, suppose the data was simulated or they were collected in the area, in a region that's different from the actual deployment of the weapon, then we'll see some extent of operational unpredictability. So when the system goes into deployment in operation, they might exhibit behavior that was not that is different from the training data. So and that can be outlier events. So there are always odd cases that was not trained, and then some kind of outlier behavior, or sometimes just because the if the mapping between the field environment and the training environment is very large, if they're very different, then the operational predictability becomes kind of low.
I see. So, you know, you have, to extend this example of a toaster, you have a toaster and it's designed to be used inside a temperature controlled kitchen, and then you take it outside and use it in sub-zero temperatures. The likelihood is that it won't necessarily perform the same way. And yet, you know, when we talk about artificial intelligence systems, you know, when they fail, they don't fail necessarily in the way that non-autonomous systems fail. Can you talk about that, the notion of how the failures are a little bit difficult to anticipate, just in terms of what the system might do when it fails?
So, so different systems, again, they have fail-proof mechanisms, right? So depending on how the system is being programmed to have this kind of redundancy or fail-proof mechanisms. But then when you have these fail-proof mechanisms, they're programmed by human designers. So they have to come up with these scenarios where the system might fail. So, and again, if the system was not trained in those scenarios, they might not be able to handle the actual failure. Actually, another interesting side of the system failure is that, let me use your toaster oven example. Sometimes it's not about taking the toaster oven from one environment to another. Sometimes it's just because the input is different. For example, it was trained to toast, let's say, you've been putting rye bread toast, and then you know what the result will be. But then in field operations, you put in a bagel, right? And you think the result would be like the rye bread toast, but its output is anybody's guess. So the input can be different, environment can be different, and then the fail-proof mechanism can be programmed and designed differently.
I see. So just one last thing on this predictability or unpredictability element. Does that mean that this sort of suggests that there's a kind of simple solution that basically you just need to make sure that your autonomous system is tested for all of the inputs that it might encounter in real life? So, you know, you test the weapon system in all the types of you know, environments that it's going to you know, to encounter.
But, yes.
Is that easier said than done? I mean, that seems like an overly simple solution, perhaps.
These days, all the AI systems, they are, you know, there's many AI systems will have a standard test set. The reason being that it's not really for safety or anything, it's for comparison. So how do you know this toaster oven works better than the other one, for example? So you need to have the same set of, same group of rye bread, and then you put them in these different ovens and you compare the output, right? So this is what we tend to have, which is a standard set or standard deployment set, standard test set for us to use and to test the system, autonomous system. Now, that's to compare different weapon systems, for example. In what you just talked about, which is the kind of a comprehensive testing in all possible scenarios, that's almost impossible. However, we can use some kind of testing mechanisms. For example, dividing the training set and a test set in different divisions, different partitions. So you take 9 parts out of the 10 for training, 1 part of the 10 for testing, and then you take another partition. So this 1 part of the 10 parts for testing and then the other 9 parts for training. So this kind of a different statistical testing method will help us also to ensure that the system is properly tested. But of course, what you want is really large data, right? So the more data you have in training, the more reliable the system will operate in different kind of environments of field tests. But maybe in weapon systems, there's a dilemma, right? Before you deploy the system, you don't have real deployment data to train it. So you might have simulated data, or you might have data from a different weapon system, and then you start with that. But you know, there are a lot of ways of trying to leverage data of different types, different genres, and to use different kind of machine learning to enable systems to do sort of transfer learning. I won't go into details, but there are a lot of machine learning methods to enable us to train the systems in a more robust manner. We want it to be robust, right? So more robust the system is, the more predictable it will behave.
Sure. No, that's tremendously helpful. So why don't we now skip to the other side of the equation, if you will, which is this notion of understandability. And for those in the audience who may not necessarily be aware of sort of the fundamentals, before we talk about what it actually means for a system to be understandable, can you very briefly just say why you want systems to be understandable?
So I think there are different scenarios. We talked about weapon systems, right? So what I learned from this community is that there's 3 levels of usage of AI systems, military AI systems. At the highest level is probably the strategic level, the generals strategizing about how to carry out the warfare. And the second level is the command level, where commanders issue orders for the weapons to behave and in certain ways. And the lowest level is the execution level, where you basically, where the systems is supposed to carry exactly the order, right? So at these different levels, I think explainability, understandability should have different requirements. For example, at the execution level, where you just have one command and then the output, it's like firing a bomb, firing some machine, and the output is pretty predictable. And then I would say the understandability requirement is not that high, because you press a button, what's going to come out of it. At the command level, you probably need to have more understanding, at least for the people issuing the commands, how the weapon system is going to behave. And that's where you need more explainability. And then at the highest level, whereas the strategic level, I think either the system has to be completely explainable to the generals, or the generals themselves have to be very, very familiar with how the system are programmed and so on. So at different level, you need different kind of explainability, understandability. But this does not necessarily mean that you need to understand each code, each line of code that goes in there. In fact, if you're using machine learning systems, the lines of codes don't really tell you how the system is going to behave. It means that at these different levels, you might have to add a separate explaining system, so explainability system, that's designed specifically to explain what kind of output will come out of, given what kind of input, right? So actually, there's a field of research where people are working on these explainable systems to run in parallel to the black box machine learning systems, to explain how it's going to work.
And just perhaps to give a little bit more context for our audience, why an explainability tool might be useful. Imagine that you have a computer vision system that is used for detecting a particular type of object on the battlefield. And in testing, it exhibits really, really high performance, right? So it has a very high level of success in identifying that type of target. But if you don't understand the system, or you don't have an explainability system, you won't necessarily know why it is achieving that high level of success, and whether it is perhaps achieving that level of success in an indirect way. So maybe it actually isn't learning how to recognize that specific object in the training data, but it's learning how to recognize all the things that are usually around that object, right? So maybe it's learning to recognize a particular type of vehicle, and it's a vehicle that is often used in desert environments. And so the system learns to associate images of the desert with that vehicle, but it would not be good at identifying that vehicle, say, in a verdant, a green environment. Well, if you have an understanding of the system, if you have an explainability tool, then the explainability tool will essentially be able to tell you, hey, this system is using the desert to identify the vehicle. It's not actually identifying the vehicle itself. And so then at the testing phase, you can say, okay, we have an issue. We need to further develop this. We can get a little bit more into some of the details of that kind of process in the Q&A, but I want to actually maybe even take a couple of steps back and talk about really what are the components that go into the understandability of the system, because not all systems have the same level of understandability. And so what are the factors that makes a system more or less understandable?
Well, we can go to the extreme two ends of the systems. So the old-fashioned expert systems, from the 80s, they were programmed with rules, and those rules are written in high-level machine language, high-level programming language, so that you look at those rules, you know what it's doing. So this is why people often talked about programming understandability, or programming values, or programming some kind of safety guards into the system. You can do that with rule-based systems. However, rule-based systems, expert systems from 80s, they're famously brittle because they are they're not able to perform for all kinds of input, right? So they're deterministic as well. So today, AI systems are largely based on machine learning or even deep learning, and they are trained on their statistical models trained on input and output data. So in that case, you know, for example, when we talk about machine vision or computer vision, in the old-fashioned systems, computer vision systems, it will be recognizing the outline, the feature, the contrasting lighting, and so on, the shapes, and so on. So you would know where the system might have made a mistake or failed, and so on, easily. But today's system, it takes the input of the image and it just figures out what are the important features by itself, and then recognize the what object it is. Now, this system itself is not gonna tell you, even if you look at the code, you don't know what kind of outline or what kind of feature it's looking at. However, it is possible to have an additional system or a small additional program to look into the different layers of the neural network and to actually extract the features that's being detected by these layers of neural network. And that would be an explainable system in the way to show you, okay, what kind of shape and what kind of outline the system is using to recognize the object. And these explainable systems, they're also very helpful when something fails, right? Because it explains the success, but more importantly, we need it to help us explain the failures so we can fix the system.
So, you know, if we can broadly say that some AI systems are more understandable and some AI systems are less understandable. Yes. And if in addition to that, we recognize that in some instances you want more understandability, that more understandability is a good thing. That raises an interesting question, which is, can you measure the understandability of a system? Can you put two systems side by side and say, this one is more understandable than that one?
We haven't seen that kind of work being done yet, because it's just the beginning when people are starting to look at understandable systems, and we have largely just looked at the features, you know, what features have been the system has been using and so on. But I would imagine that also, if you cannot also compare, let's say, rule-based systems against the statistical systems, because their performance are so different. Statistical systems perform so much better that there's no comparison to the rule-based systems. So usually, it is depending on the application and the particular system or weapon system you're using. Even in AI in general, you know, depending on what kind of chatbot you are using, some are very, some are rule-based, so you know what it's gonna say, but these rule-based systems are not gonna be able to answer or chat with you about everything you say because the coverage is very bad, right? Because they were designed previous, you know, by hand, by humans beforehand, so if the humans didn't think of certain kind of input, it's not going to be able to handle it. But statistical systems, on the other hand, can handle any kind of input or any kind of things you say, and then it will be able to provide an answer back. So when we compare these systems, we often compare performance, not so much as understandability, because we're first and foremost concerned with performance, then we come to concern with the understandability.
No, that's extremely interesting, and you know, I'm sure it's of great interest to those involved in the discussion on lethal autonomous weapon system. This question of whether it may be one particular avenue to think about whether understandability can be measured, because that potentially could be useful in looking at one system versus another system and saying, well, you know, this one has, you know, might be more, could be used more prudently potentially because it's more understandable than that one. But you know, from what I've seen from the literature, you're absolutely right. It seems like the measuring of understandability is still at a fairly early stage. It also raises an interesting point that part of the reason you may not be able to measure the understandability of the system is because the level to which a system can be understood is partly dependent on the person who's trying to understand it.
Right.
Now,
right.
I have no background in the technical aspects of this technology. I imagine that you have a much higher capacity for understanding a system than I do. A system that to you is fairly understandable, probably to me is completely indecipherable. And so, you know, from our discussions, we've also talked a lot about how, you know, figuring out who the person is a big factor here as well, right?
Right. And I would say in the deployment stage or operational stage, understandability is perhaps less important than predictability. So if you know what kind of how the system is going to behave, just knowing that give you control, give you some kind of sense of control. You might not need so much understandability. So these two concepts might you know, can interact with each other when you're operating a weapon system. I mean, it's not realistic to require an AI engineer to be the sole operator of these systems. It could be a soldier, it could be a military personnel, and so depending on their background and the requirement, so perhaps you don't always focus on understandability, but perhaps more on predictability. So they know what to expect. That's more important than they know how the system is programmed or how the machine learning works.
So, you know, in a sense, what you're kind of getting at, and this is something that the report touches on as well, is that it'll be really important to figure out what is the appropriate level of predictability and understandability for every given instance, right? Where it'll be a question of trying to figure out what are the requirements, to use a more sort of technical or military term, for understandability, and that is one potential direction. Before we head into the questions, I just wanted your thoughts on one last point, which is, you know, what are some of the technical challenges that need to be overcome in order to make these systems more predictable and more understandable? You know, we can all say, yes, these systems should be fully predictable and fully understandable, but it seems like the reality is a little bit more difficult. And so I was just wondering if you could mention what some of those research challenges are looking forward.
Well, on the data side, on the training data side, the challenge will be if you don't have enough training data. So either the training data, this is not large enough samples, or if they're skewed to one kind of behavior only. And then another challenge is if you don't have real data, you have only simulated data. That's gonna raise a lot of operational predictability issues. And then we don't have a standard metric of safety and accuracy measure. We need to have an agreed upon standard to measure safety and accuracy, right? We need to standardize these laws as we do with conventional weapon systems, right? And these standards should be governed by, you know, various Geneva Conventions and also meet the consensus of member states. So different, so the stakeholders have to get together, the military, the civilian, the member states, to and the engineering, to work on this set of standards of safety, accuracy, and what kind of training data, how much training data, simulated or not, these kind of issues, and that will be very important. These will be very important factors lead to the predictability outcome.
Yeah.
Of the outcome.
No, that's incredibly helpful, Pascal. And with that, I think we can wrap up our discussion and hear a little bit from the audience. So we do have a number of really fantastic questions coming in. Again, for audience members, if you do have a question, please type it using the Q&A function, and we will try to get to as many as possible. Now, there's a first question actually that I might just resolve very quickly, which is that an audience member pointed out that we've been using the term understandability, but also the term explainability, and whether there's a difference there. And this was a conscious decision actually with this research project to use the term understandability. And that is because while explainability is a much more common term in the debate on lethal autonomous weapon systems, in the technical community, explainability often refers to a more narrow set of systems that you, Pascal, were referring to earlier, these systems that will help explain a black box system. It also doesn't necessarily help that explainability makes it sound like a system is kind of like a human. It's assigning human agency to a system as though this system can explain itself to you like a person could. And so we felt like a broader and all-encompassing term that refers to both the intrinsic, transparency of the system, as well as any features that it might have added on to explain it, could be better encompassed by the term understandability. So to our dear audience member, I hope that does resolve your confusion on that. We have a question here.
There are many.
From Colonel Emmanuel Camarillo from the Permanent Mission of Mexico. And he asks, how can autonomous military weapons give full confidence to the civil sector or to policymakers that the weapon is fully prepared to not violate human rights and also to respect international humanitarian law? In other words, can we have a system, can we achieve a level of trust in these systems that they can comply with all of those rules? What would you say to that?
I would say that, for example, recently or maybe a couple years ago, IEEE standards has issued a set of design guidelines to align with human values. So I think it is possible to provide a set of design guidelines of these systems to be aligned with the various international humanitarian laws, as you mentioned, and then to ensure that the outcome are complying with these standards and laws. So we just incorporate these, these laws into the design guidelines.
Mm-hmm. Another similar question that may shed even perhaps a little more light on this notion of trust comes from Eduardo Sanchez. And Eduardo is asking about fail-safes. He asks about whether there can be fail-safe provisions added to autonomous weapons that are making life and death decisions, and whether that might be a way, as I interpret the question, to reduce the unpredictability if you have a fail-safe.
You mean like a hard restart button kind of thing? Or
well,
do you mean,
I mean, when you think about adding a fail-safe on a system, what does that really mean? And does that have a role in the development of autonomous systems?
I'm sure there is a role for such fail-safe designs, absolutely. Because depending on what the system is used for, I'm sure the designers can come up with scenarios and together with the users as to under what circumstances, therefore, for these machines to operate beyond which threshold that it should be it should not be allowed to fail. So it's kind of determining the threshold of performance, and also I would say it also gives a backup human control. So it's kind of a fully autonomous, wherever it's possible, that you can have a fully autonomous system reverts to human control. Kind of like the, these automatic flight systems that will allow manual control. I would imagine something along that line can be designed as well if you want to have ultimately human decision rather than machine decision.
Mm-hmm. Our next question comes from Larry Lewis. He asks, you have focused on machine learning here, which is just one type of artificial intelligence. We have been using other types like Bayesian statistics in weapon systems for decades without a debate on predictability. And so Larry asks, why do you think that predictability is such a debate right now? What do you think we can perhaps learn from past artificial intelligence applications?
Actually, to me, Bayesian statistics is a kind of machine learning. Machine learning doesn't mean it's a neural network or deep learning. So to me, that's still a kind of machine learning. Having said that, I think a lot of the predictability issue came up in recent years precisely because a lot of AI systems incorporating deep learning have done an incredible job, and then it became more visible, and therefore there are more discussions around them. And I think this is why. Secondly, also because people are much more aware of ethical issues, because having seen real life applications more upfront, right? And decades ago, civilians or lay people wouldn't even know what's behind those systems, let alone what AI is. But today, people see autonomous drive, for example, driverless cars crashing and so on. So people are more aware, more knowledgeable about these issues. So there's a debate, and I think it's a good thing. And how can we learn from past AI applications? I think a lot of things can be learned from past AI applications. First of all, not everything needs to be designed from scratch. I wouldn't break anything that's, I wouldn't fix anything that's not broken, so to speak. But on the other hand, a lot of AI applications in the past, for example, in my field of speech recognition and natural language processing, machine translation, and so on, have taught us the importance and correlation between training data, testing data, marginal cases, outlier cases, and so on. I think we can learn from those experiences and these applications how to design our future systems and for it to be more safe and more accurate.
No, absolutely. I think there is actually a lot of material out there that can shed a lot of light on this discussion. And that was certainly my experience in putting together that report, is that especially in the civilian sector, a lot of these issues have been discussed at length, and perhaps they feel kind of mysterious and novel for those debating autonomous weapons. But in areas like autonomous vehicles, self-driving cars, AI for medicine, a lot of these issues have been debated to quite a great extent, and with some results even to push things forward. I want to try and get to a couple more questions. This one comes from Maya Brem at the ICRC. She asks a really interesting question. Is there a sort of universal agreement in the science and technology community about the meaning of understandability and explainability, or are there differing definitions?
I think in the community, depending on which AI area, so is it the natural language processing area or the computer vision area or so on. So there's some kind of agreement, and there are also differences between these communities, because they concern themselves, we are working on different tasks. So computer vision feels like, community might need certain kind of explainability, understandability, whereas a machine translation system, nobody really asks about explainability and so on. So depending on the application and the community. And again, this is a field that's really emerging. The study of explainable systems and understandable systems. I would say they're more explainable. People use the term explainability more, explainable systems, than the understandable systems. I think probably because to a lot of the AI researchers, every system is understandable because we design them. So it's like explainable. You see, one is understandable by the people who are using it or designed it, but explainability, we have the impression that we need to explain what we have designed to the users. So that's more of a focus in the technical field. And what are the advantage? Yeah.
I think that's really helpful. Again, going back to this notion that it so much depends upon who is trying to understand the system. I want to get to maybe two more questions before we wrap up. This question from Amelia Jaworski is a question that I've pondered a lot as well, and would be really interested for your thoughts, Pascal, which is, what are the considerations of predictability and understandability in the context of adversariality, the notion that people are going to try and mess with your autonomous systems, and that might have an effect on them. You know, is this something that might have an effect on the understandability or the predictability of these systems?
Yeah, I would say yes. I would say yes. Yes, the focus is different. So the design, the focus of design will be different, and the training data will be different, and the measure will be different. It's a very, very good question, because I think this is particularly important to the area of autonomous weapon systems, right? So when we talked about AI system falling into the wrong hands, this is nothing's more nothing's more pressing than the issue of what if there are adversarial use of weapon systems. Yeah, so I am not involved in manufacturing or designing any of the systems, but from a general technical point of view, I would say people will be, so you could design systems or simulation systems that will attack the system, the weapon system, try to hack it, try to attack it, try to make it, and so on. So you can design such systems or design such scenarios as part of your holistic design of your weapon system. I would say this is probably very, very important for all kinds of weapon system design, isn't it? To incorporate these adversarial attacks and adversarial design and so on.
So I just want to fit in this one very last, very quick question before we wrap up, which comes from Carl Chang. He says that he's curious to learn more about Dr. Feng's reference to the IEEE design guidelines. You know, can you please point him to where he can read more about that?
Okay, it's the IEEE, I think it's ethically aligned design. You can Google that term.
And it's a fantastic resource. I've drawn on it.
Yeah, they have a document on ethically aligned design guidelines. And I think they're very, very, very good. And but there are other IEEE. I'm part of a IEEE, one of the IEEE standards group, working groups working on AI standards. So there are a number of those to various details. So guidelines, and then you have standards, right? And then you have these metrics of measure and so on. So there are different levels, and various IEEE groups are working on them.
Well, with that, and it really breaks my heart to say this because I'm seeing so many more fantastic questions coming in through the Q&A, but that is all we have time for, folks. But because there is clearly so much interest in this topic, because in this 45-minute discussion, we can really only scratch the surface of what is a tremendously significant and complex issue. I want to end by saying that this should really serve as the start and not the end of a discussion. And as I mentioned, we have just put out this report, the Black Box Unlocked, that will hopefully answer a number of the questions that we didn't get to today. But more broadly, you know, we really want to be in touch with you, and we want to talk about all of these important issues and these questions that you have. And so please don't hesitate to be in touch with us here at Unidir. That's what we're here to do, to serve the policy and the research community as it tries to grapple with these issues. So we stand at the ready to serve in whatever way we can. Before I wrap up and thank you, I just want to say finally that we have a very brief feedback survey that if you so wish can fill out for this event. It takes literally 30 seconds. That you can find the link in the sidebar right now. I hope you've enjoyed this discussion certainly as much as I have. Pascal, thank you so much for spending some time with us today. I wish we could talk sooner. I wish we could have had you over here in Geneva, but we'll have to put a rain check on that and maybe have you around next year. But thank you so much. This has been really fantastic. I've really appreciated it. I'm sure everybody else has. With that, we will sign off. Thank you all so much for joining us, and enjoy the rest of your day. All the best.
Thank you.